Let's look at charged particles moving in a magnetic field. If you recall, current-carrying wire in a magnetic field experiences a force given by this formula. Okay. Well, if you can think about a charged particle, they say a proton or something like that, right? A charged particle in a magnetic field. Let's have the magnetic field maybe be out of the page here, right? A magnetic field. A moving charge is like a current, okay? So there's going to be a force on this particle, and we can actually derive it, right? So force is I LB sine theta, right? Current is just Q divided by T, right? So we've got some charge Q. So force is Q over T, that's our I, right? Times L times B sine theta, right? And then we can use the commutative property of, I don't know, I can move that T underneath the L, right? I can go F is Q times L over T times B times sine of theta. And of course, a length divided by a time, in other words, the distance it travels, right, is just a velocity. So you end up with that the force on a moving particle is QVB, right? And this is, of course, in the right-hand direction. Okay, so what that means is that your index finger is in the direction of V, right? Your middle finger, the way I do it, right, is in the direction of the magnetic field, and your thumb of your right hand will be in the direction of the force, okay? Except that there's the exciting possibility that the charge could be negative, and then of course you get a negative force in that direction, or I prefer to just say negative charges experience a force opposite the direction of positive charges. At least that's how I would do it, okay? And we'll talk about that in a little bit here. But anyway, there's the basic idea. So the velocity is meters per second. The Q is, of course, in coulombs, right? The force is in newtons. And anyway, there we have it, right? Now, let's think about this force, right? If we put our index finger this way, okay, and I put my middle finger out of the page, because these dots represent the magnetic field, right? That's out of the page. Okay. If I do that, I get a force, a magnetic force that's down this page, right? Well, it's at right angles to the velocity, so it actually doesn't speed up the particle. Forces at right angles actually cause it to change direction. So what this thing's going to do, if that's its velocity, this thing is actually going to turn to the right, as if we're looking forward, right? It's going to turn like this and go in a circle. That force is by its very nature a centripetal force. So we'll calculate the force just all by itself. And then I'll show you how to solve for the radius of the circle it goes around and all of this good stuff. Okay. So here is, let's say, a proton, right? Okay, this proton's in this magnetic field. It's a positive charge, right? So basically we'll have protons and electrons, right? I'm not going to give you tau particles or something like that, right? This particle is moving this way. This is its velocity, right? So put your index finger that way again, right? Put your your middle finger. This is the magnetic field, right? Okay, that way, right? And of course, this is going to go. The force will be this way, and it'll cause it to go in a circle like that. Okay, so this thing will literally the force will always be toward the center. Sorry about my oval circle here. Okay, but anyway, there it is, right? So the path of the particle will be a circle. We'll get to that, but let's do some of these other problems first. Okay.